So let us continue the ripple counter or asynchronous counter. So now suppose I want to design mod 6 counter. Okay, mod 6 ripple counter or asynchronous counter. Now you have this mod 6 counter. Okay, so obviously you need 3 flip-flop. Okay, so I'm using this time T flip-flop instead of JK. T flip-flops. Okay, T flip-flop. So T flip-flop will be what? So you have 6 state, so you need minimum 3 flip-flops. One, let me make space. Okay, and you have one more flip-flop. Okay, so these are T flip-flop working in a toggle mode, that is J equal to 1, K equal to 1. So I am making the toggle 1 T flip-flop. Okay, they say this is my Q1, this is Q1 bar, this is Q2, this is Q2 bar, Q3 bar is the output of this one. Okay, now since this is a asynchronous counter, so what you need to do, say this is your negative triggering counter, so output of 1 become the clock for other. Okay, so this is basically your ripple counter. Okay, now what I want to do is you're giving clock here. So this counter has total 6 state. Okay, so let me make the truth table for this one. So you have Q1, Q2, Q3. Okay, and then you have a clock. Okay, now 3 bits means there are total 2 state. Okay, but we need only 6 states. Up to 5 we need only. That means remaining the remaining bits or remaining state. Okay, we have to truncate. Okay, or we have to reset. For example, when clock is 00, so we should get 00. Okay, when clock is first, I should get 001 state. When clock is this, I should get 010 state. When clock is 3, I should get 011. When clock, and here I'm putting a reset parameter. Okay, because I don't want the, I want the state to reset. Okay, the 4 will be what? 4 will be your 100. Now 5th will be your 101. Okay, now this is mod 6 counter. It can have a state from 0 to 5. It can count up to 0 to 5. And up to 5, it should again come back to the 00 position. Now what happens when 6th pulse comes? Okay, when 6th pulse comes, then it goes to 6th state, but we do not want this 6th state. Okay, we want this counter to count only 5. Okay, so my 6th state momentarily should come. My 6th state should be 000. Are you getting? My 6th state should be 000. Okay, that means this state 110, they may arise. Okay, but then we have to make this 1 and 100, and this is already 0, so no issue. Okay, so this state should transform 110. Okay, I'm writing here. When 110 comes, okay, momentarily, then it should reset become 000. Okay, so here the reset parameter is 000. This term I don't want to reset, so R is 0. This term I don't want to reset. This term I don't want to reset. This term I want to reset. Okay, so I put 1 here. Now what is the meaning of this? This will be clear in a minute. Okay, now as soon as 110 terms comes, a parameter, okay, Here I am putting now clear bar, a asynchronous input. Okay, asynchronous input, you know what it does. Whenever you give 0 to this clear, whenever you give 0 to this clear, it will make the clear. Okay, it will make the output clear. That means it will make the simultaneously make the output of everything is 0 0 0. Okay, so now here the reset parameter should be attached with this one, is all the clocks. So when you give this 0 reset parameter 0 to clear, okay, this will set the all the queues 0 0 0. Okay, so I'll tell you what to do, how to do this one, how it will count. Now the next state, when you seventh pulse will come, okay, again you have 600, again you get 001, and this will be continue. Okay, it will state will be repeating. Eighth you get 0 1 0. Okay, you don't reset parameter, you don't want reset parameter, so this will be continuously counting. Now up to it is clear. At this point should be clear. Okay, then I can talk other things. Okay, now you see this counter is counting up to 5 only. After and when it is 6, it is reset parameter is 1. Okay, and then other 7 is not coming, 8 is not coming. Again they are repeating. That means 7 8 for this counter. Total state is remaining states, all the remaining states are don't care conditions. Okay, for example, if I want to make a truth table, I want a value r. R is function of q1 q2 q3. Okay, so say this is q1 q2 q3. Now I should have 8 state 0 1. Okay, so first state r is 0, second state r is 0, third state r is 0, 0 state 1. Okay, and then 2 3 everything is 0 0, 4 is 0, 5 is 0. Okay, when 6 comes, 6 is a 1. This is 6 7. 6 is a 1, and 7 does not exist. 7 is a don't care condition. Okay, 7 is a don't care condition. So up to here, sixth state will come momentarily. Okay, and we have to reset this one. So sixth state we have reset. So we have 1. After that, this is just a repetition. So all the 7 8 all other things are your 7th up to 0 to 7. 7th is your don't care condition. Okay, now I want to get, this is my what, this is my 0 1 q1 bar, this is my q1 0 0 0 1 1 1 1 0. So I want r. So what should be r? Okay, so for r, what should do? Only this I can take. If I take this one, this will be equal to what? q1 into q2. Okay, so obviously here you have q1 q2, this is already 0, you have to reset only q1 q2. Okay, now let us see how we can do it. Okay, now you want q1 q2 to reset. Just 1 minute. Is coming q1 q2 or q2 q3? So q1, okay, this is q1 and this is q2 q3, 0 0 0 0 for this term. You have what? You have this 1 1 q2. Okay, q1 q2. Okay, so let us take a q1 from here. Okay, and let us take q2 from here. Oh, make them send them to NAND gate. Okay, so NAND gate will give you r bar. Okay, so whenever these are 1 1, okay, so output becomes 0, and this output 0 you attach to this clear input. So this is a clear input. Okay, now just look at again this all the state. Okay, whenever this combination this become 1, okay, multiplication, so you can see this is the only one term where q1 q2 is 1. Here q1 q2 0 0 0 0 0 0 0 0 0 0 0. So I'm trying to say up to 6th only there is this one combination. For that, this R can be 0. There is no other combination for that R bar can be 0. Okay, how? If you put 0 0, then it is 1. If you put 0 0, it is 1. Okay, so when clear is 1, when clear bar is 1, that means it is not operating. So in order to make reset, you need to give 0 to this clear bar. Okay, so clear bar 0 means it clear is 1. So when you give 0 only, then only it will reset. So even though you are putting this q1 q2 value here, for this term, this term, this term, this term, this term, this term, it will not reset. It will reset only when this multiplication become 1, and that happen only for this state 1 1 0. As 1 1 the state will arise, this multiplication will become this will 1 and this becomes 0, and you can see that. So you put a clear bar as a input, it will automatically reset every q1 q2 q3. Okay, now just if you doubt, please ask me.
सर
हाँ,
अगर क्लियर बार 0 करेंगे मतलब क्लियर 1 होगा तो ये रीसेट
रीसेट
होगा।
रीसेट हो जाएगा, अदरवाइज
ओके
रीसेट नहीं होगा। ओके, सो फॉर इस स्टेट के लिए 0 0 है तो रीसेट नहीं होगा। ओके, क्योंकि ये क्या ये वन आ जाएगा। इस स्टेट के लिए भी 1, इस स्टेट के लिए भी q1 q2 आपका ये जो मल्टीप्लिकेशन है 1 है 1 है 1 है 1 1, ओनली इसी स्टेट के लिए ये 0 आ रहा है। ओके, नैंड गेट का आउटपुट 0 आ रहा है, तो ओनली इसी स्टेट को वो रीसेट करेगा, बाकी स्टेट को रीसेट नहीं करेगा। ओके, सो नाउ दिस इज योर रेडी, दिस इज योर काउंट mod 6 काउंटर। ओके, नाउ लेट मी ड्रॉ दिस ट्रुथ टेबल फॉर दिस वन। इसको मिटा दूं क्या? 0 0 1। ओके, सो व्हाट इज शोइंग q3 q2। इसको टेबल को सॉल्व करने पे देखो क्या आ रहा है, सही आ रहा है कि नहीं आ रहा है? So okay, correct. So I am putting this is q1 q2 q3. Okay, so I am telling this is q3, my q3 q3 q2 q1. Okay, it is correct. ये ठीक है क्या? So this is 0 0 1 1 1. Okay, I think this should be correct. Okay, now let me make the table for this one. Now you are giving a clock. अभी क्लियर हो जाएगा, आसान है ये। So this is you are giving clock. This is clock 1 2 3 4 5 6 7. You're giving 8. Okay, so 9. Okay, now q1, this is a negative tracking clock, so q1 say initially 0, this become up here, this become down here, this become up here, this become down here, this become up here. Okay, now what happens when 6th comes? When 6 comes, become down. This is your q1. Okay, and this is your this one. Okay, so I want to reset what? q3 q2 q1. So okay, one mistake we have done while making this truth table. Okay, I told you this is my MSB, this is my MSB, and this is my LSB. Okay, so while I make the truth table, okay, when we make the truth table, I have written this is q1 q2 q3. Okay, so just make it this q3. q3 q2, that's q1. Just replace this q1 q2, and now r is your what? R is your q3 q2. When I solve the truth table, my r is q3 q2. That mistake we have done. Okay, so r is your q3 q2. Okay, now I want to make this will keep on going 7 down. Okay, 8 up and down. Now q2 will be when 0. Okay, q2 will be this will be the clock, so it come down, it will go up, it come down, going up. Okay, it is coming down, is going up. Okay, Now what happens at 6? What happens at the 6th? It goes up, it goes 1, but after momentarily, because we have reset parameter, so it will go up and then it will come down. At 6th clock, okay, your Q2 will go up, okay, and then it will come down, and then it again becomes 0, okay, and again it will go to 1 here, again 0, again 1, okay. Similarly, if you see Q3, okay, Q3 will follow this one. So this is down, so clock is go up, okay. Now Q3 will follow this one. So here it is getting down, so it will come like this, okay, and again it will go down, so it will go up like this. It will work. Now you can count, okay. So initially you have 0 0 0, okay, this is 0 0 1, okay, after clock 1, after clock 2, this is 0 1 0, that is 2, after clock 3, this is 0 1 1, after clock 4, this is 1 0 0, nicely going up to 5, this is the 1, this is a 0, this is a 1, after 6, after clock 6, momentarily it become 1, but now again it becomes 0, okay. So it becomes 0 0 0. So after 6, you again the terms repeat 6 7. After 7, you have 0 1 0, okay. Sorry, 0 0 1, 0 0 1 should be there. After 0 0 1 should be there, okay. Let me check this one. Momentarily come up and then go down, okay. So after 6, this momentarily go up and then it's come down here, okay, and this is 0. So this is 0, this is 0, this is 0. Now here 7th it should read 1, okay. So what is the mistake I'm doing here? 7th is coming down here, okay. Here we have missed the trick, na? Here we have mixed, okay. This is going here, this is going up here, this is going up, this is going down here, this is going up here, okay. So here it's going down, it's going down, up and down again here, and here nothing will happen. It will change here, okay. When it's coming down, it will change here, and like this it will go, okay. Similarly, if I see this one, nothing will happen here, this will go like this. So 7th 0 0, after 6 7 6 0 0 0, after 7 0 0 1, okay, after 8 0 1 0, like this it will keep on moving, okay. You should just remember that negative triggering clock, whenever is coming, the previous input is coming down, other will change. So this counter only will count up to 0 to 5, okay. So this is easy. If you still have confusion, please you can ask me, we can discuss, okay. So your R is basically Q3 Q2 here. So whatever you want to reset, you should identify the parameter, okay. That parameter you want to reset. So the other things are same, everything same. So Nandana, Radhika, Lakshmi, is clear or not?
Sir, we can use only T flip-flop.
Huh?
T flip-flop only we can use.
T flip-flop, other flip-flop also we can use, na? We can use D flip-flop also, no issue, okay. Because here asynchronous, there is no issue, because this this control is with us, okay. How it should change, we can decide, na? We can use D flip-flop also, we can JK flip-flop also, but T flip-flop means what? T1 means what? J equal to 1, K equal to 1. So you can put JK also, there you can make 1, okay. So there is no issue here. Counting state, no issue, okay. Now when you do this mod 10 counter, you'll automatically understand what I'm doing now. You're not just make mod 10 counter, okay, using same method. So you need to identify what is the value of R, where you want to reset it, okay. This plotting is very easy, okay. Just first we'll make state table. First thing is you have to make the truth table, and you have to identify the reset parameter. Once you know the reset parameter, automatically things will be clear, okay. So now here you mod 10 counter, that means you need at least 4 flip-flops, Okay, that we'll discuss later. First you make the table. Okay, Q3, Q2, Q1, and then you have to make clock. Okay, clock is 0, you want 0 0 0 state. Okay, then next state should be 0 0 1, 0 0 1. Okay, for clock 2, 0 1 0. Okay, for clock 3, 0 1 1. For clock,
यहाँ पे
huh?
4 आउटपुट्स नहीं होंगे, 4 फ्लिप फ्लॉप है तो
Very good. That's very good. That's 4 should be. There are 4 flip flops. So you should make Q4, Q3. Okay, because we want to go up to 9, na? So we need 4. Very good. So I want Q4, Q3, Q2, Q1, clock. Okay. So the first thing is clock 0. So this will be 0 0 0. Okay. Then I want clock 1 0 0 0 1. Okay. Clock 2 0 0 1 0. Clock 3 0 0 1 1. Clock 4 0 1 0 0. Clock 5 should be 0 1 0 1. Clock 6 should be 0 1 1 1 0 0. Okay, clock 7 should be 8. 7 means 1 0 1 1 1. Okay, and you want this one. This is correct, na? This is how much?
no sir 0 1 1 0
0 1 1 0. Okay, and 8 is your 1 1 0 0. 9 is your what? 1 1 0 1. Now this becomes 10. So already 10 is state. Okay, now 10 should not come. Now next state will be what? Next state will be 10. Okay, 10 means 1 1 1 1. But this should not become.
Sir,
Okay.
1 0 0
Huh?
0 नहीं 8
क्या?
1 0 0 0
क्या
8
चीज?
1 0
0 0.
0 0
Okay.
then 1 0 0 1
1. Okay. और 10 में क्या आएगा?
1 0 1 0
1 1 0 1 0.
0
Okay. So this is your 10. Okay. Now 10 स्टेट आनी नहीं चाहिए ना, क्योंकि हमारे पास तो mod 10 है, तो 0 से 9 नहीं आनी चाहिए, 10 आनी चाहिए. 10 क्या हो जाएगी? रीसेट हो जाएगी. So 10 will come momentarily. So 1 0 1 0 will come momentarily, and that will become 0 0 0. Okay. So I'm writing here 1 0 1 0 will come, but it will transform to 0 0 0 0 0 0. That means now Q3 0, Q2, Q3, Q4, Q3, Q2, Q1. Okay. Now we have to reset this combination Q2, Q3. इसको 0 0 बनाना है. So Q4, Q2. तो हमारा R जो आना चाहिए वो Q इस केस में Q2, Q4 आना चाहिए. तो हम चेक कर लेते हैं. इसी को रिसेट करना है. This time is 0. This time is 0 0 0 0 0 0 0 0 0. Only here it is 1. And another condition after you go 11 12, that will be your, and don't get conditions. Okay. So let me make now R. Okay, for R, so you have a Q4, Q3, Q2, Q1. Okay, all the parameters are now you have 8, 16. Okay, so you have 16 now. Four. Okay, so all are 0 0 0. Okay, you have only 10 10 1. So 8 9 10 10 is 1. Okay, these are 0 0 0 and 11 12. 11 is your roadmap condition. 12 13 14 15. Okay, so 0 1 3 2 4 5 7 6 8 9 8 9 10 11 12, 13, 15, 14. Okay, so 4, so all other will be don't take condition, you have only 1. Okay, now you, this is 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay, solve this one. What will come? Tell me what will come.
Sir, 11 will also be don't care, na?
Levels also I'll be also don't care condition ना.
So तो 12 हो गया, 11.
ये 12 है कि 11 है?
12 है सर.
ये 11 है.
Yes sir.
Okay,
तो quad बन जाएगा.
क्वाड बन जाएगा. वेरी गुड. ये क्वाड बन जाएगा. तो R क्या हो जाएगा? इस क्वाड में Q2 आपका कांस्टेंट है और इधर में आपका इस क्वाड में क्या कांस्टेंट है? Q4 कांस्टेंट है. तो Q2 Q4 और Q2 और Q4 को ही ट्रंकेट करना है. Q2 Q4 को ट्रंकेट करना है. ओके, नाउ ड्राइंग इज वेरी इजी. ओके, ड्राइंग के लिए क्या करना है? जैसे पहले किया वैसे कर दो. 4 फ्लिप फ्लॉप बना के T को 1 1 कर दो और क्लियर बार लगा दो एक इनपुट और उसको R से कनेक्ट कर दो. सबको R से कनेक्ट कर दो. सो ए सिंक्रोनस काउंटर आसान है बनाना. ठीक है, सिंक्रोनस काउंटर बनाना आसान ही है, बट एक बार आपको प्रैक्टिस करके बार बार देखना पड़ेगा. क्योंकि एग्जाम में तो क्या, एग्जाम थोड़ी ऐसे पूछेगा. एग्जाम में तो आपको काउंटर बना देगा, आपको आइडेंटिफाई करना पड़ेगा फटाफट से कि कौन सा काउंटर है, कौन से बिट का काउंटर है. थोड़ा सा उसको एनालिसिस करना पड़ेगा माइंड में क्या हो रहा है. पूरा करने जाओगे तो टाइम लग जाएगा. सो लेट अस मेक द काउंटर. ओके, डिजाइन. सो you have 4 flip flops. Okay, all are negatively triggered. You're giving clock here. This is T flip flop. T is 1. You're giving T1. T is here. You're giving 1 here. T. You're giving 1 here. Okay, then you have Q1, Q1, Q1 bar, Q2, Q2 bar, Q3, Q3 bar, Q4, Q4 bar. Okay, this will become clock for this one, this one become clock for this one, and this become clock for this one. Okay, now you have clear bar, asynchronous input, clear bar. This is your clear bar. This is your clear bar. Okay, now you want Q2 Q4. Okay, so take Q2 and Q4. Okay, and take a NAND gate. Here you can take Q2 and Q4. R bar will come. Okay, Q2 Q4 ka bar, and this Q2 you can connect to disconnect you all the things, this all the clear bar. Okay, you can make nicely, you can make one line attached to this one. Okay? Just you need to connect this output to all the asynchronous inputs. That's what I'm trying to say. Clear hai? So this was your asynchronous input. Now we'll talk about the frequency limitation of asynchronous counter. Okay, because asynchronous counters are connected in series. Okay, their clocks are connected, so the delay will be keep on adding. So if delays, each flip flop has a delay. Okay, because flip flop is basically made of what? Logic gates, and logic gates are basically they are fabricated by transistors or diodes. Okay, which have some capacitive effect. So as soon as you give input, okay, the output will not come at that particular moment. Okay, their output will be delay output. Okay, so suppose you are giving an input, that output will take a little bit time, so there will be delay between input and output. So because there are n flip flop, Okay, so there will be n delay, and if delay is keep on happening, it has a chances that counter may miss some counting. Okay, suppose you are mod 10 counter, okay, and after pulse 8 it should count 8, okay, but it may count 9. It may miss the number 8 because of the delay, propagation delay of each flip flop. Okay, so let me explain this one. So put the propagation delay in ripple counters. Okay, propagation delay in asynchronous or ripple counters. Now, for example, I have a clock. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay, keep on going. Okay, now I have this outputs Q4, say Q1, Q2. Okay, yes, Q1, Q2, Q3, Q4. Okay, now when Q1 is coming, there's a negative triggering clock. So when this clock is coming, this will change the output, but it will be this change will be a little bit delay. So there it should happen here. Instead of happening here, this will happen here. Okay, so this will happen here. That means at this particular time, okay, there is some delay. Just give me 1 minute. This should be okay. So let me make this like this. Now this is your propagation delay. Propagation delay is written by TPD. So you get 1 TPD delay here. Okay. Now this will be continue. Okay. Again it will go down. It will change here. Okay. So this is your actual should be here, but it's not happening here. So these are my transition points. Okay. Okay. Now it will happen here a little bit. Similarly, this delay will be continue. This is called delay of 1 flip flop. Okay, it's become like this. Okay. Now second terms comes Q2. Okay, this will transit here. They should transit here. Okay, but because now second flip flop will also get delay, so instead of happening here, it will happen here. So now there's a delay of 2 flip flop, 2 PD. Okay, so it will happen now up to 2 PD. Okay, so instead of happening here, it will happen here somewhere here. So this is delay of 2 flip flops. Okay, so this will happen here. Again, it will happen here, and again it will happen here. Okay, so now you have output is keep delaying. Okay, now for example I'm giving Q3. Okay, so Q3 will come again like this. Okay, and Q3 will become change here. Okay, so now you have for third flip flop you have a delay of 3 TPD, propagation delay. Okay, so this will become down. It should happen here. Okay, 1, 2, it should happen here. Okay, it should be happening here. Okay, and then again it should happen here, it should happen here. So if you keep on moving like this, what will happen? You're going Q1, Q2, Q3. Okay, at the number of flip-flops increasing, okay, this delay will be keep on increasing. So there is a possibility, okay, that this time period, okay, become lesser than the delay. If delay become the delay of and flip-flop add together, it became greater than the time period of this clock. So what will happen? Automatically this one count will be get missed. Okay, so suppose counter supposed to count 8, but it will count 9. Are you getting my point? Because each flip-flop has a delay. Okay, now if this delay keep on happening, so transition which suppose should happen here, okay, that will not happen. That will happen to 9. That transition will happen for your 9th clock. Are you getting? See this delay here, I want transition. Okay, so this is now going 0. So here it should become 1, but it suppose it is not becoming 1 here. This 1 is becoming after your 9th clock. Okay, then this counting miss, na? Okay, just understand this one. Okay, and now I'll give you question, then you understand. Okay, so because this propagation delay will keep on adding, so where transition should take place, the transition will not happen. Okay, transition will not happen. So this delay, this delay and TPD, suppose there are n transition, delay will be n TPD. Okay, that will become greater than the time period of this clock. Okay, and then become time greater than time period of clock, one of the term will miss. Okay, it will not count. Okay, so because of this one, okay, your ripple counter has a limitation of maximum frequency. Okay, because you cannot have any random frequency, high frequency you can apply. Okay, if you apply high frequency, time period becomes small. So time period becomes small. In that condition, what will become? This delay will be greater than your time period. So that there will be miscounting. So there is always a limitation of the frequency of this ripple counter. Okay, so what is that one? So I'm using this one. So basically, your time period of clock should be greater than your n TPD. Okay, where n is the number of flip-flops. Okay, and this TPD, this is your propagation delay time of one flip-flop. Okay, now TC should be greater than n TPD. That means 1 by TC should be less than 1 upon TPD. Okay, and 1 by TC is nothing. This is FC. Okay, so your FC has a clock frequency has a already limit. It can maximum, it can be equal to n TPD. Okay, should be less than actually, but just to calculate the upper limit, we can make it maximum. Okay, so this is the limit of upper frequency for your ripple counter. So for example, the question is there.
सर सर डिले टाइम जो होगा वो ऐसे मतलब उसका भी कुछ होगा कि हम मतलब कैसे पता चलेगा हमें कि इसका डिले फ्लिप फ्लॉप का टाइम इतना है?
वो क्वेश्चन में दे रखा होता है ना।
ओके,
जैसे अभी जो मैंने आपको बताया टीपी लिख दिया, आपको क्लॉक का टाइम दे दिया है, क्लॉक का टाइम सपोज 0.5 सेकंड दे दिया, ओके, टाइम पीरियड, और आपको दे देगा डिले टाइम 0.1 सेकंड है, तो वो 0.1 सेकंड 0.1 सेकंड 0.1 सेकंड आगे आगे ऐड तो जाएगा, ठीक है।
यस सर,
और जब आप प्लॉट करोगे तो आप देखोगे कोई काउंटिंग मिस हो गया है, जब ड्रॉ करोगे सिग्नल को तो आपको पता चलता है कोई सिग्नल हो गया है। अभी जैसे मैंने बोल दिया कि 0.5 आपका माइक्रो सेकंड आपका क्लॉक टाइम है और 0.5 माइक्रो सेकंड आपका डिले है, तो फिर तो बहुत जल्दी काउंटिंग में मिस्टेक आ जाएगा, दो काउंटिंग के बाद ही एक क्लॉक मिस हो जाएगी।
यस सर,
ठीक है, ओके। सो दैट्स व्हाई इसकी फ्रीक्वेंसी इतनी रखनी है कि टाइम पीरियड हमेशा इससे ज्यादा ही रहे, ओके। नंबर से जितने भी काउंटर, जितने बिट काउंटर है उसकी फ्रीक्वेंसी इस फॉर्मूले से डिसाइड होती है, अदरवाइज वो प्रॉब्लम करेगा काउंटिंग में, ओके। So for example, it says question, for what minimum value of propagation delay in each flip-flop a 10-bit ripple counter skip a count when it is clocked at 10 megahertz. Okay, so they have given you 10-bit ripple counter. Okay, and they say the frequency of ripple counter. Okay, at clock frequency is given fc 10 megahertz. Okay, then says what is, for what minimum value of propagation delay. Okay, so they are basically asking you TPD. What is the value TPD so that it will miss one count. Okay, it will skip one count. What should be the value of, what should be minimum value of delay, okay, for one flip-flop so that it should skip one count. Okay, so it will skip one count only when your FC equals to n TPD. Okay, so to that they are asking you TPD, that will be your 1 upon n FC. Okay, n is given already 10-bit triple counter, so this is 10. Okay, FC is given 10 megahertz, 10 into 10 to the power 6 hertz. Okay, so this become how much? 6, 7, 8, 10 to the power minus 8. Okay, or you can put 10 to the power 10 minus 9 and minus 9 seconds. Okay, that will become 10 nanosecond. 10 nanosecond. Okay, so the relationship should be 10 nanoseconds. Okay, correct. Okay, so this formula is clear. The more the number of flip-flop, more the delay. Okay, more the flip-flop, you have to reduce the frequency. Okay, if you have a 3 flip-flop, you may have some frequency, maximum frequency. If you have 6 flip-flop, then the maximum frequency will be keep on reducing as the number of bit ripple counter bit increases. Okay, so for example, it's the same question. If I say 3-bit ripple counter, okay, and the frequency is this one, so then how much TPD should be there? Tell me, for 3-bit counter. Or I'm changing this question. I'm saying giving you TPD now. I'm giving you TPD equals to 10 nanosecond. Okay. Now 3-bit ripple counter. What is the maximum frequency of operation? 3-bit ripple counter. What is FC? Tell me. And you find this should be greater than 10 megahertz. Calculate. So TPD is given 10 nanosecond. Okay, you want to calculate FC for 3-bit triple counter. Okay, so you have 3 here, and this is 10 nanosecond. This is 10 power 9 upon 30. Okay, so if I put this is a 1000 megahertz upon 30, this comes 00. If you divide 30.33 megahertz. Okay, so automatically if you reduce the number of bit, okay, the operating frequency increases. If you increase the number of bit or number of this flip-flop, the operating frequency decreases. So that's why these, if you have a, and this why we say that ripple counter is a slower counter. Okay, because because of this limitation. You cannot apply high frequency. Now, next the heading synchronous counter. So synchronous counter definition we have already discussed. In synchronous counter, the difference is that your all the flip-flop is be triggered by simultaneously by one clock. Okay. So now there are some steps. Now you want to design a synchronous counter. Okay. So there are some steps you have to note down. Okay. So put the heading design of synchronous counter. Design of synchronous counter. Okay. So number one step is there. Okay. You have to count. Okay. How many number of flip-flops are required. Okay. By seeing this one, step one. Okay. Go to how many numbers of, okay, how many numbers of flip-flop required. You have to first decide. Okay. Step two, you should make the phase diagram. Okay, state diagram or phase diagram. You have to make state diagram. Okay. So state diagram will tells you that how your states are moving. Okay. For example, you want to make up counter, down counter. Okay. So it is varying from 0 to 9 or 9 to 0. How your states are moving. Okay. How you want to count. Okay. And from this is not necessary to 0 to 9. Okay. There may be some intermediate, some any random states also. Okay. So basically you should know from where to where you want to count. Okay. And how you want to count, up counting, down counting, that will be decided by state diagram. Okay. You have to fit the logic how you're counting, that you should first decide. Okay. And once you know this state diagram, step 3, you have to decide. Okay. Which flip-flop you are going to use. Okay. Flip-flop type, whether you want to use D flip-flop, SR flip-flop, JK flip-flop. So once you have number of flip-flop decided, then you have to decide the flip-flop type, and then you have to decide and you have to write the excitation table of that flip-flop. Okay, excitation table of flip-flop, excitation table of flip-flop. Okay, now once you have decided excitation table, now step 4, what you have to minimize the K map with logic. Okay, you have state diagram, and accordingly you want to find the inputs of this flip-flop. Okay, so you have to minimize the K map. Okay, and then the last step is draw the logic circuit. Okay, step 5. Okay, draw the logic circuit. Okay. So state diagram means that we'll discuss this, like you are going from 0 to 7. Okay, or you're going 7 to 0. That diagram you have to make. Okay, flip-flop type, you understand what is the flip-flop type. Now let me first tell you what is the excitation table, which is very useful to us to write the truth table and minimize the K map. Okay, so you should know the excitation table of every flip-flop. Okay, this we have already done. So now put the heading, what is excitation table? Excitation table for different flip-flops. Okay. So इसमें क्या एक सबका मेथड सेम ही है. Once you know one type, designing of one type of synchronous counter, आप दूसरा अपने आप कर सकते हो. Now what is excitation table? Okay, excitation tables tells you how to change the states. Okay, for example, if I have a present state, okay, Qn, and next state Sn. So I have a Qn and I know Qn plus 1. Okay, and I have the variables S and R. Okay, so this is the excitation table for SR flip flop. Excitation table for SR flip flop. Okay, so suppose you have 0, 0 to 0, 0 to 0 to 1, 1 to 0, 1 to 1. Okay, so these are only 4 possibilities. Okay, you have 0, 0, 1, 1. Okay, so how can you go from 0 to 0? How can you go from 0 to 0 in a SR flip flop? Okay, so 0 to 0 is what? Your no change condition, and your reset condition. Okay, so no change condition, so is 0 to 0. So this is for S0, R0, and reset condition is what? S0, R1. So R is varying, S is fixed. So you can write 0x. So we have already done this one. So you have to just remember. Now similarly, 0 to 1, when can appear? 0 to 1 can appear for S equal to 1, R equals to 0. Okay, set condition. And what is the other thing? Okay, 1 0 only. So this is your 1 0. Okay, similarly, this is your reset condition. Okay, and 1 1, this is your no change condition and set condition. No change condition and set. So 1 0. So this is the truth table for your SR flip flop. Okay, similarly, you write for JK flip flop. If you have a JK flip flop, okay, you have present state, next state, then you have Qn plus 1, and then you have a JK. Okay, so you have 0 0 0 1 1 0 1 1. Okay, only 4 possibilities are there. Okay, now tell me what is the J and K value? SR, D and T. Okay, tell me the variables. So in JK flip flop, 0 0 condition happens when?
No change condition, sir.
Okay, so what should I write here?
0 1.
Sure.
0 0 0 0.
0 0 is no change condition, and reset condition is also 0 1. Okay, so 0x. Clear? Same thing, ना? अभी ऐसे तो आएगा 0 1. Okay, 0 1 is set condition. So I can write what? I can write as a 0 to 1. So 0 to 1 happen in set condition. Okay, that is 1 j equals to 1, k equals to 0, and 0 to 1 also happens for toggle condition also. That is j equal to 1, k equals to 1. Okay, so you can put j equals to 1 and k equals to x. Okay, 1 0 1 0 again happens for toggle condition, j equal to 1, k equals to 1. Okay, and 1 0 happens for reset condition, that is j equals to 0, k equals to 1. Okay, so j is changing, k is 1. Okay, 1 to 1, that is your no change condition. No change condition means your j is 0, k is 0, and this is also set condition, j equal to 1, k equals to 0. So this will be like jx. Okay, so 0 cross 1, 1 cross x1, x1, x0. So this is the excitation table for JK flip flop. Okay, why I'm writing this one? So whenever I give you this type of combination, 0 to 0, what inputs are required, you can immediately tell me in this one. When I ask you what is the require, if I'm using JK flip flop, what are the, for this kind of transition, what are the inputs required, you can tell me immediately. Okay, so that you should remember. So whenever I will do synchronous counter, and if I'm using JK flip flop, so you have to keep this table one side. Okay. Now similarly, if I want to use for say D flip flop, excitation table for D flip flop. Okay, so D flip flop means you have only one variable, D. Okay, so D flip flop is like a SR flip flop only. Okay, so what happens? Tell me the table for D flip flop. So 0 0 happen only for this
Zero.
one, and 0 1 happen for
1.
1. Very good. And 1 to 0, 1 to 0 is what? Reset condition. That is 0. 1 1 0. Clear? Sorry. 1 1.
No, the into mark.
It is correct. If you have 0, okay, 0 0, that means you want S0 R0. Okay, that is your D0. Okay, S0. Automatically this one. Okay, you want 0 to 1, that one you want D equals to 1. That is correct. Okay. Now if you want D10, 1 to 0 reset condition. Okay, reset condition, S should be 0, R should be 1. Okay, that is S is D, so D should be 0. Okay, 1 to 1. Okay, 1 to 1. So 1 to 1 happens only your set condition. Okay, no condition to है नहीं इसमें, set condition है. Set condition happens for S equals to 1, that is D equals to 1. It's correct. So already I have made a truth table for all the things. From here, there you can check and you can identify. Okay. Now similarly for T flip flop. Okay, T flip flop. Okay, so make T flip flop. So in T flip flop, what is the table? Okay, so I'm writing here required inputs. Okay, so this is basically required inputs. These are required inputs. Required inputs. Okay. Required inputs. So 0 0 you want 0 1 1 0. Okay, this is the excitation table for T flip flop. Okay, so we'll learn tomorrow. Okay, so I'll stop here. So if you have any question, please ask. Excitation table you should learn, okay, by seeing the state, what are the variable which will make this transition to happen.